When we go from solid to liquid, liquid to gas, or solid all the way up to gas, or maybe we go from gas to a solid, gas to a liquid, liquid to a solid, what we're doing is we're undergoing a phase change, or we're changing the state of matter that something is in, right? So when we go from solid to gas, we're doing a sublimation, gas to solid, deposition. Solid to liquid, we're melting. Liquid to solid, we're freezing. Liquid to gas, we're evaporating, and gas to liquid, we're condensing. So we go through all of these different changes as we change the state of matter. When we're undergoing these phase changes, we're not changing the identity of our sample in any way, shape, or form. We're just changing the state of matter that it's in. Okay? Now, every substance has what is called a specific heat capacity. So it's the amount of heat required to change the temperature of 1 gram of the substance by 1 Kelvin, or by 1 degree Celsius, okay? These are exactly the same regardless if we put it in terms of Kelvin or Celsius, because when we deal with these, we're going to be dealing with a change in temperature. And the size of a Celsius degree is the same as the size of a Kelvin. And so when we do a temperature change, the magnitude of that change is exactly the same in Celsius and Kelvin. So let's say I went from 0 degrees C up to 100 degrees C, okay? My change in temperature is my temperature final minus my temperature initial. 100 minus 0 gives me 100, okay? If I do this in Kelvin, 0 Celsius is 273.15. to 373.15, well, 373.15 minus 273.15 gives me 100, okay? So sometimes you'll see these specific heat capacities in joules per gram degree Celsius. Other times you'll see them in joules per gram Kelvin. Kelvin, Celsius, because it's delta T, they end up working out the same, okay? So here's some specific heat capacities. All right, so we've got aluminum, copper, and water. Well, if you look at liquid water has a really high specific heat capacity. This is one of the reasons why water is so interesting, is that hydrogen bonding in water gives us this really high heat capacity. And this is important because the higher the heat capacity, the more energy it takes to change 1 gram of a substance by 1 degree. And so if water had a lower heat capacity, then it wouldn't be able to withstand all the temperature changes so easily. And our bodies are mostly water. So we wouldn't weather temperature changes nearly as easily as we do if water had a lower specific heat capacity. So, okay. All right. So we have our phase changes. All right, so here, this is a heating curve. We're going to go from ice at negative 25 up to 0. So we're going to warm that ice up. So our temperature is changing there. Now, once we're at ice, it doesn't immediately turn into liquid. If you take ice out of the freezer, it takes some time before that ice melts. So what happens is the ice has to go from whatever temperature it was at up to 0 degrees Celsius. Once it's at 0 degrees Celsius, then it can melt into water. So no temperature change is happening here. We're just intaking some energy. Once all of my ice has melted to liquid water at 0 degrees, then I can change the temperature again and heat it up to the boiling point, which for water is 100 degrees Celsius. Once I'm at the boiling point, now I can begin the phase change from liquid water to water vapor. And once my water vapor is all formed, then I can take my vapor and heat that up. Okay, so at some points along this, we are undergoing a phase change. At other points along this, we're in one phase and we're changing the temperature. Now, if you look, the line to go between ice and water is a lot shorter than to go between water and vapor. Why? Well, think about those intermolecular forces. If I'm going from a solid to a liquid, I'm just letting things move around. But if I'm going from a liquid to a gas, I have to break those intermolecular force tethers. And it takes a lot more energy to break those tethers than it does to just get things to move around with each other. Okay. This is showing it in the opposite direction. But if you start over here at this point, you can see, so here's my solid. It's all nice and close together. Okay, once my solid is heated up to its point where it undergoes the phase change, now you can start to see we've got some particles that are close together, but some particles that are still kind of solid, so we're going to undergo that phase change. Once we hit the phase change, then now we're all in one phase, and we can change the temperature. And then once we get to the next stage, then now we start converting our liquid to our gas. And then once we get all the way to gas, then we can start raising that temperature. We can also go back the other direction. If I start off with a whole bunch of gas, I can get it to condense down. Once it condenses down, I can lower the temperature, I can freeze it, and then I can lower the temperature further. Now, as we go along this, all right, we have several different things that we have to take into consideration, okay? So I have this equation line here, okay? So Q is my heat, M is mass, C is that specific heat capacity, and then delta T is change in temperature. And then I have some delta H values. Okay, so I have delta H of fusion and delta H of vaporization. Delta H is enthalpy. Okay, and so if I'm in one phase, then I'm going to use a specific heat capacity and the change in temperature to figure out what's going on with my amount of heat or my amount of energy. If I'm undergoing a phase change, if I'm going between solid and liquid or liquid and solid, then I need this delta H of fusion. I need this enthalpy associated with that phase change. How much energy does it take to get the phase change to go? Okay, once my phase change is undergone, then I'm back to my MC delta T again, where now I use my specific heat capacity and I change the temperature. Okay, and then once I get to the next phase, then once again I use that delta H. This time it's the delta H of vaporization because I'm going between solid or liquid and gas or gas and liquid. Okay, and so you can see here I've got my melting and my freezing. Okay, those are using the delta H of fusion, the vaporization, and the condensation uses the delta H of vaporization. And then if we were going straight between solid and gas or gas and solid, we would use a delta H of sublimation. Now, the reverse process is condensation, freezing, sublimation. Those all have a negative delta H. The numerical value is the same. The amount of energy it takes to melt something is the same amount of energy we get back once it freezes, because it takes energy to get something to melt. So it's an endothermic process. But getting it to freeze is an exothermic process. It's getting rid of excess heat. And so it's just the opposite amount. Okay. All right, and then we've looked at this once before. This is again showing us that heat of vaporization so much higher than the heat of fusion because it takes a lot more energy to break those intermolecular force tethers than it does to just get something that's solid to start moving around like a liquid. Okay. All right, so let's do a couple examples here. So we've got an ice cube. We're going to take that out of the freezer. All right. So it comes out at 0 degrees Celsius. It's going to melt, and then it's going to sit out on your countertop, and it's going to get its temperature raised to 18 degrees Celsius. So we want to know the total amount of energy absorbed. So two processes are happening here. One, we're going to melt the ice, and two, we're going to warm the water. Okay, so melting, that's a phase change. Okay, and that's where we're going to use the mass times the delta H. Okay, and this is a phase change going from solid to liquid, so that's the delta H of fusion. Okay, our next one, to warm the water, this is not a phase change, this is a temp change. And so that's where we're going to use the MC delta T. So to get the overall Q, we're going to take mass times the delta H of fusion plus that MC delta T. So we're going to add the two processes together, and that's going to give us our overall change. So now we need to take a look at these tables. So first we're going to need the delta H of fusion, okay? So I have two values on here. I have one in joules per gram and the other one in kilojoules per mole. Well, when we look at our equations here, we're using mass, right? Mass is done in grams, so we're going to want the joules per gram. So we've got the heat of fusion and the heat of vaporization. This one we need the fusion, so we're going to use this 333 joules per gram. Okay? Now, we're going to take that ice and it's going to melt, so it's going to become water. So when we do process number 2, we're warming water. So when I look at my specific heats for water, do I want the specific heat of ice, the specific heat of water, or the specific heat of steam? Well, I want the specific heat of water because that's the phase that we're in, is we're in the liquid water phase. Okay? All right, so let's calculate this. All right. Oh, would help if I changed the color back from what I was just doing. All right, so we have 3.50 grams of water times our 333 joules per gram for our delta H of fusion, plus we still have the same sample. So we still have our 3.50 grams because it just melted. Nothing happened to it. It just went from solid to liquid. So we still have our same 3.5 grams. All right, so we have our 3.50 grams. Our specific heat of water is our 4.184 joules per gram degrees Celsius. And then our change in temperature, we had 18 degrees Celsius minus 0 degrees Celsius, so 18 degrees. All right, so remember, this is the melting, and this is the warming. Okay? So when we calculate that, we're going to get 1,429.09. Okay, in our problem, our temperature was given to us at 0.0 degrees Celsius. So two significant figures there. So we're going to get 1,400 joules because here grams and grams will cancel, leaving us with joules. Grams and grams cancel. Degrees Celsius and degrees Celsius cancel, leaving us with joules. So your heat should be in joules. Okay? All right. Now, you want to make soup, but your water's not running. You only have some ice left in your freezer. So you want 92.4 grams of ice, and you want to heat that up to its boiling point. But then you forget about it, and you can't make your soup because you let it all go to steam. This is what my husband would do. He would start his pot of water boiling sometimes, and then he would walk away from it. All right, so what happens? How much energy does it take to take that ice from 0 degrees all the way up to converting to steam? So you're going to have three processes. You're going to melt. Okay. You're going to warm. And then you're going to vaporize. All right, so again, melting, that's a phase change. That's where we use the M delta H. Warming is a change of temperature. That's where we use the MC delta T. And the vaporizing, that's a phase change again. So we use that M delta H again. So for the melting, we're going to use the delta H of fusion. And for the vaporizing, we use the delta H of vaporization. Okay? So you try it. Take a look at the numbers I have here and see if you can grab the correct numbers and you try the problem. All right, let's see how you did. All right. And again, it's the same mass throughout the whole thing because our sample doesn't change. Okay, so there's our melt. And our change in temperature was 100 degrees. And then here is our vaporizing. Okay, and so when you do it all, you should get 275,000. Sorry, I cannot read my own handwriting. Okay, and then we have 2 sig figs again, so we're going to take this to 2.8 times 10 to the 5th joules. Okay. All right, and here's one more. Okay, we're going to heat something up that starts off at 25 degrees, and we're going to take it all the way to steam. So our two processes, we're going to heat, and then we're going to vaporize. So again, heating, change in temperature, vaporizing, change of state, and we're going to use that delta H of vaporization. Okay. So again, try it before moving on to the next one. And then notice though, it does say the final answer needs to be in kilojoules. Okay. All right, let's see how you did. Okay, so we're going to the 4.184. And then we did the 100 minus the 75. Or not 100 minus 75. It turns out to be 75. It's 100 minus 25, sorry. Okay. And then we add to that. Okay. Then we get 38,097 joules. Okay, we wanted the answer in kilojoules. So we have 1 kilojoule for every 1,000 joules. So we get 38.1 kilojoules. All right, so that is how we deal with problems where we're trying to figure out what's going on as we are changing phases. Water's easy because we know the melting and boiling points of water, so those are easy to know, where we're going in between our phases because we're used to dealing with water.